who also have no background in weaving. So for quite some of you, I assume, if you are already in a master or further, that you might have already seen or had courses on weaving, and then a large part, of course, will be repetition. But in the second session, then we will go to the practical work with TextGen, which which probably for most of you will be completely new. But so first we need to go over the standards of weaving to get the terminology correct. And this is material, as you can see from myself, from Professor Liva van Langenhoven of Ghent, and from Jiwan Lee, also from Ghent, who have been working on the material you see, combined with resources from the internet. So as said, Razvan already showed this, the module on design and modeling of woven structures is built up around 5 cases. So in the end of this year, there will be a training also in Ghent when woven structures will be the center point. And then the idea is to go over all 5 cases. In this shortened version that we are having today, I hope to be able to go over cases 1 and 2, perhaps case 3 also, depending on how easy and how fast the presentation can go with the software then. So I will be giving here in this theory section the background on how to use, so that you should be able, by listening to me, to do then the tests that are in the online course for case 1, 2, and 3, because there are also tests present in the Moodle course. So the first 3 cases are on the standard woven structures, as you should know them from the textiles you are wearing. It goes over more complex yarns used in, for example, smart textiles, and moves on to 3D woven structures, which are used in technical textiles, composites, etc. Case 4 is on how can we import these structures, these woven structures, to Abacus and do a simulation with them. And case 5 then is going more deep in how complex woven patterns and coloring is made in practice on weaving looms, so as to obtain a specific result. Okay. Now, before we begin, as we need to do software, you will need to install the TextGen software on your computer for the practical work at 11 o'clock. So this is a Windows package. You can download it from the link which is here. So perhaps I should paste this now in the chat. So I pasted this in the chat. If you go, so it's under here somewhere. Let's make it smaller, because I can't see it with the WebEx. So this is the TextGen website. It's from an English university professor who has made this. And if you go to the SourceForge project TextGen, you see the latest version, which is now from last year, version 3.12.2. And the software you would need is the complete bundle, typically, the one that is here. And on a standard Windows box, this should then just work. So please download this, have the installation run in the background while you are following here the presentation on the background and the weaving material. TextGen itself, so yeah, for the Ghent students, they all had lessons from me, so they are looking forward to the next days and the afternoon session, because that will be mostly new material. They have TextGen already, but so for the other ones, TextGen is an open source software under the GPL, so everybody can have a look at the code and do further development on it. It's made by the University of Nottingham, and it is used to model the geometry of textile structures The default that is present in it is for the modeling of woven structures. It is, however, perfectly possible to make knits, to make complex structures, as you see here to the bottom right, which is a non-default woven structure, let's say. But if you do those, you need to interact with the software through a Python scripting. So you need to program the structures you would want to have, and then TextGen can create them. The geometry, the things you make with TextGen, can be used for investigation, so as to have an idea of how things, what they look like, and can be imported into IGES or STEP format, which are formats which can then be used in simulation computer-aided development software. So you can then continue with it. It is not a software for visualization of woven structures, and that is the case 5 has that, but we will not be handling that case today. So weaving, where does weaving come from? There was already weaving by humanity from 5000 BC. You see here an image from some temple in Egypt, where you can see already a weaving loom, a vertical weaving loom or horizontal. It's always difficult to know with the Egyptian iconography how they work, but you see how they are having yarns, how they are putting gaps into a woven structure in order to create a fabric, which you can see is finished at the bottom. It's rolled up, whereas at the top you see all not yet woven yarns being stretched. So these are the vertical yarns or the warp yarns. They are pre-present. Now, by 700 AD, horizontal and vertical looms were widespread throughout Europe, throughout the world, I assume. And by the 12th century, there was a mechanism that you had a hand-operated shuttle and a feet-operated heddles. What does that mean? You can see here to the right an image from a manuscript, a medieval manuscript. And you can see the feet are operating what is called the heddles, and they connect to parts of the yarns that can be moved upward or downward. And you can see that the person sitting here has in his right hand a little piece, which is the shuttle, in which another yarn is present, which is passed through the gap that is made into the warp yarns. And the hands, they push, they throw, let's say, the shuttle from one side to the other side. And then with the feet, they every time can create different structures so as to arrive at a woven fabric. Now, everything went a lot faster in the 18th century with the Industrial Revolution, where you suddenly have huge halls full of machines making very kilometers of fabric in a go in order to satisfy the requirement of humanity to start to use textiles more and more and more. And woven textiles were the first technique that allowed to create huge quantities of fabric. Nowadays, this is also possible with other techniques, but originally not. So weaving itself, it is done on a machine, which is called the loom. And the person who is weaving is called the weaver. And this here is an example of a more modern machine, which can work as good as independent, autonomous of an operator. And it can do 1,000 picks per minute. A pick is where you bring a yarn from the left side to the right side in such a machine. And 1,000 picks per minute, so this is several ones per second. So this goes so fast you can hardly see it. You cannot see it with the naked eye. Now there are many types of weaving. We can divide it over dimension. And if we divide it over dimension, then the most woven structures that you will know or the 2D woven structures. It means that if you put the fabric on a table, it's as good as flat. So we call that 2D weaving. You have yarns running from left to right and from bottom to top, let's say, if you have an XY system, and that's it. And the thickness, you can measure it, of course, but it is not really playing a role. Whereas you also have 3D woven structures. There's an example given here to the right. They are complex structures which nowadays become more and more common for creation of use cases for technical textiles. And these 3D woven structures, the Z-axis, so the thickness, here you also have this X and Y, the 2D dimension, the Z dimension becomes really important and is used in the functionality of your fabric. You also have a division over yarn orientation. In that case, we speak about biaxial, multi-axial, and polar. So this is mostly referring now to the 2D woven structures. The standard 2D woven is biaxial. So it's like on a machine like this one. But there's also multi-axial, like triaxial. You can see that in nets that are woven still, where the angles over which the yarns are placed running not just in X and Y, but also along diagonals or on other angles. And you also have polar, which is a sort of multi-axial, and then the black lines you see here to the right are woven into it. Yeah, so it's a polar structure, and yarns are added over the radius in that case. Now, in order to have the terminology correct, so we speak about warp yarns and weft yarns. So the warp yarns are the ones which are present at the start, and they are just here in this image. They are the red yarns, the red lines, which are stretched from bottom to top, and they are loose. They are not connected to each other. And then the weft yarns are the yellow yarns, and they interlace. And the normal interlacing is the biaxial, so under 90 degrees, and it is brought into the, if we say it starts at the bottom, it's brought in between the fabric, and then a next line, etc., so that you have a full structure. So how is that done? The warp yarns are under tension. We have here that the warp yarns are connected to two frames and the heels, and the frame can move upward or downward. In this case, the first frame is brought upward, the second frame is brought downward. This creates a gap, which is the shed, and the weft yarn, in this gap, the weft yarn is placed through the gap via the shuttle or via another mechanism. And by doing this after each other and doing the weft yarn, in this case, the weft yarn is brought from left to right and from right back to left. So this is with a shuttle. Then you obtain in the end a woven material. If you look at it for multi depicted here on this slide, where several frames are used so as to bring weft yarns to very specific gaps, so that different types of gaps are made in order to arrive at the 3D woven structures. But many 3D woven looms are quite different from this, but this is the extension of the standard loom to create a 3D woven structure. Now, once the weft yarn is brought into this shed and the shed closes again, this weft yarn will be not very nicely placed in a fabric. It will be, because it's brought through an opening, it will not be aligned to the left, close to the intersection point of your warp yarn. So in order to make sure that here you see the shuttle, it moves through a gap, this moving through the gap is, let's say, 2-3 centimeters away from where the fabric is. So this has to be beaten up. So here you see what is called the reed. With the reed, the weft yarn is beaten up, so it is adjacent to the already made fabric. This is an important part in weaving, and the consequence of this is that typically the warp yarns have quite some tension under it, but the shuttle is, the weft yarn is placed into it, the shed goes closed, and this will create some tension, of course, also in the weft yarn, but not as much, and then the beating up happens. So it's mostly the strength is more in the tension is more in the warp yarns than it will be in the weft yarns, because they are not kept under full tension as you do the beating up. Okay, if there are any questions, feel free to ask. So as you can see here, the warp yarns are around a beam on the left, which is pre-prepared. This is it takes a lot of work to make such a warp beam. And on the right, another roll rolls up at the same speed, or a higher speed, or a lower speed, depending on the tension you want in your final fabric. And it is the fabric roll that will be your final fabric then at the end. So this is the principle. Once you have a fabric, there are several fabric parameters to take into account. One of them is the density. The density is the weight that you have of your fabric per surface area. So it will be a unit in gram per meter square. You can cut out a part to test what your density of your fabric is. So it's a different density, because the thickness of a fabric is often not very accurately defined. Yeah. We typically talk about weight per surface area and not per volume. The warp density is the number of warp ends per unit length of fabric. So how many warps you have per centimeter per meter. The weft density is the same in the weft direction. It should be clear that this can be very different. Your warp is preset, and with your weft density, while you loom, you can still play with this. The crimp is also an important parameter that you find that is often talked about. The crimp is the length of the fabric over the length of the yarn when it is stretched. So if you take a piece of fabric and it's, let's say, 1 meter on 1 meter, then if you take out a warp yarn, this 1 meter of fabric will be in warp yarn perhaps 1.2 meter. So this fraction, 1.2 over 1, sorry, 1 over 1.2, is your crimp. So it shows how much of the fabric it becomes smaller by being into your fabric. And you have that for the warp direction, and you will have a different one for your weft direction. And it will depend on how you are weaving, how big this crimp is. You need that, of course, if you want to compute how much yarn length you will need to weave a certain structure. And this structure has so much length, so you need to take this crimp into account in order to calculate how much yarn you will be using for your fabric. The cover factor gives you the relative space that is covered by the fabric. So it's like your shadow. If you would do a lamp on your fabric, you would see shadow and then some light, if it would be not too hairy, your fabric. So this is the cover factor. So if you have a lot of warp density and a high weft density, your cover factor will be very high. And then you have the interlacing ratio. This is how many times your warp and weft interlace with each other over the maximum possible interlacing points that there are. And so some structures are woven very loosely and then have a low interlacing ratio. Now, once you have the fabric, a lot of properties are of high importance for companies and you want to have control over, and it might be due to the weaving that things go good or bad. A typical fabric properties looked at is the strength of the fabric you have at the end, the appearance. So you see here in the image that there are quite some loose structures and parts not woven very equally. So one would not want to have that. The ravel, how easily parts unravel at the edges, for example, the snagging, the wrinkling behavior, um, and the permeability. This is important for how much it can be air permeability or vapor permeability. So how easily the wind penetrates your fabric or moisture penetrates the fabric, etc. Those are all fabric properties that are looked at, but this is more general, of course, than woven structures. Also knitted structures or non-wovens will this be investigated, but woven structures have for many applications a lot of advantages. They typically have a higher strength than the other materials that you can make in other methods, and the permeabilities, you can go to very low permeabilities, typically with woven structures, which is a lot more difficult with non-woven or knitted structures. So what are the basic weave structures? The most basic one, the one that was shown in the image also before, is the plain weave. And so the plain weave is that you interlace every time. You go over, if this here is the weft yarn goes over the warp yarns, under, then over, then under, then over, then under. So you get the typical checkerboard pattern. This is the most simple structure. You have, however, very high intersections. And typically in these structures, the warp density is much higher than the weft density. And a reason of that is, of course, because the yarns have to go up and down every time. So there has to be a gap between the weft yarns for the warp yarns to go up and down. And that this creates this difference in density. Now, a plain weave, if you look at the top or the bottom sides, they will be fully identical. So it's not possible with a plain weave to get it very dense in one direction or even in both directions, because you every time need this interlacing of, every time need space for the yarns to move up and down within the structure. Now, common way, one of the most common woven structures is the twill weave. In the twill weave, you can see that you go over, you have longer floats. So if white here indicates that the weft yarn is on top of the warp yarn, then you see that you go over three warp yarns before you go under one. And this creates what this is called a float. So you have a longer float, you have less intersections, and you arrive at a more open construction than a plain weave fabric. And here is an example. What you typically see in twill weaves is not anymore a checkerboard pattern, but you can recognize it by diagonal lines that are present. Of course, these kind of patterns, this checkerboard and these diagonal lines, they are only very obvious if the color of the warp and the weft yarn is different. If you are using the same colors, then it becomes much more difficult to just recognize by the eye what woven structure is used. And then another very common woven structure is a satin or sateen weave. It is given by, it is a little bit, so where the twill weave creates the diagonal structures, in a sateen weave, this is more randomized and not close to each other. So because of that, you can make it denser. It's often used for uniforms protective clothing, etc. Those are the basic woven structures. And then you have some special structures also, and of the special structures, the Lino woven structures are quite common. And in the Lino weave, you use a slight change in how the loom is operating so that you can have a rotation. So you see here, you have your warp yarns are the red and the blue, and the weft yarns are, let's say, the gold. And you open the shed, the warp yarn goes through, but then the blue yarn goes to the left of the red yarn, and then for the next weft again to the right, again to the left, again to the right. And because of that, you can keep a very net-like structure. You can create a structure which is very open, very stable, and which is more like a net as opposed to a standard weave. And because of this, let's say, almost spiral type of structure, the weft yarn is kept into its location and is not moving up and down. It has, of course, a very good impregnability. It's often used for let's say, mosquito nets, those kind of constructors, for bags, for curtains, where you don't want to use too much material. So you can have a very open structure, but it still has to have strength and rigidity in that regard. Okay. But then you can have, once you have this set up with woven structures, you can make a multitude of materials, and you can use several post-processing techniques, and you have combinations of this twill, of this sateen, all with different types of names, which would require you quite some studying in order to know all the terminology that is used. Look, here, for example, at the bottom left is a roll calendared. It's a woven structure. It is quite open, so it would probably not be very stable. The yarns would move, but the calendering is used, so a hot roll is rolled over the fabric as it is made, and the hot roll fuses it a little bit at the interconnecting points, which allows again to have a nice stable woven structure. Now let's go in a bit more detail, because if you're using TextGen, you need to indicate it, and also because when you are doing technical textiles, you have to be very aware of the different woven structures and how much this influences your final fabric properties. So the plain weave, we have seen, the plain weave is just every time up and down. You have several variations on this, which are given here. One, the warp rib, the weft rib, the mat rib. So in the warp rib, instead of doing every time an interlacing, as in the plain weave, you cross with your warp yarns, 2 weft yarns, and you go under 2 weft yarns. So you have a 2-2 structure in the warp. Whereas in a weft rib, you have a 2-2 structure in your with your weft yarns instead of your warp yarns. Yes, and in a mat rib, you do the same in weft and warp. So you in this times under, and the same if you look at the weft yarns. Often this is depicted with crosses into a grid, and it can be regular or irregular. So an irregular structure here is, for example, 2 times over the warp yarn goes 2 times over a weft, 3 times under a weft, 2 times over a weft, 3 times. So this interlacing, it is like a plain weave, but it is done in an irregular way. Yes. Now for twill weave, you also have a lot. I said in a twill weave, you typically have these up and these diagonal lines that come forward. So in this case here, the image given is a twill weave where we go with the warp yarns and the weft yarns over two warp yarns at a time. So it will be a 2-2, I assume, twill weave. And then you can make variations on that, and you can go zigzag, where you get these pointy structures. The zigzag is also called the pointed or the wavy twill. And you see that you just reflect the twill at a certain vertical axis, and then instead of moving from left to right, you go from bottom to top, you go from top to bottom. Yeah. You can shift, instead of having these points interconnect in a zigzag, you can, at a axis where you inflict, you can move up so it becomes broken. This is called a herringbone twill, as given here. And then you can see that immediately, if you look at these fabrics, the structure, on one hand it's the same, but yet it seems completely different. Yes. And then you can do that. You can not only inflict on a vertical axis, you can also inflict on a horizontal axis, and then you obtain these diamond twill structures. And they exist depending on how many yarns you cross before you interlace again. You get all kinds of different results from that. If you then go to the Sateen weave, a standard satin is given here. The image is an irregular one, where here on the left side it seems quite irregular already. Here you see that sometimes it's close, sometimes on the image the interlacing points are farther away. So the main thing is, as opposed to a twill where it keeps on going along a diagonal, here in a sateen it is split out. Sateen is from English. Many languages don't have two words. Satin is if it is done in the warp direction, and sateen is a satin in the weft direction. In English, they make this distinction, and you have then regular and you have irregular structures. Yes, now there is a visualization software. I could show it, but it is an old software, not anymore on the market, and it only works in 800 times 600 screens, so I would not try it here. I could, if somebody wants to see it in action, I could show it during the break or during the questions. So what this is you have a woven structure. You say what your unit cell is. This is an amount of warp and an amount of weft. So in this case here on the left, it's 18 warp, 6 weft. And then you can say with the black and the white. So black is, for example, where the warp yarns are at the top, and white is where they are under a weft yarn. You can create structures, and then you see what the effect of that is in your final woven structure. You just repeat this at a specific zoom level in order to investigate what the effect would be from doing a specific structure. Now with the satin and sateen, here is an irregular sateen weave, and you can see that you have crossings in an irregular way and not connected to each other along diagonals. And you see here again to the right hand side what the result is. So we can do that a bit ourselves. I would say let's do that. So to see once an example, I will put this here in the chat. So this is a Google spreadsheet. You have read access to it, and you can just download it. If you click on the link, you will see that there are 3 tabs with the sketch structure. So with the black square, you indicate the warp goes over the weft. With the white square, the weft goes over the warp. And then you can add a symbol in a cell to make it black. Yes, so if you download that, that will also work. It will work in Google Docs, or it will work in Excel normally without problems. So the point is, if you put here an X and you do enter, it becomes automatically black because there's a condition set on it. And with delete, you can remove it again. And so I would say this is a herringbone pattern that is made in that way. And I would say make ones. Let's take one of the examples here. Let's see. I try to make one of this set. I try to make once the conditioning of this satin weave. Yeah. So do that. And so for the satin weave, let's see. And the main point always, if you do that, is to find the repeating structure that allows you to quickly do then copy paste to speed up the process. So I assume this is possible for everyone. If you have problems with this, just let me know. So this gives you, without the software, just by using a spreadsheet, an idea on how the advantage here is, of course, you can also change this rule in order to obtain other colors. And so, and this is with this conditional. If the cell is not ready, we can change our color. That's also the cell, the color of the, yeah. Now, once you have a structure with a repeating one, you can create a new see. You can further edit this. We now need to find where the column sizing is. I thought this was easy. Format. Okay. So you can do the format of a column. So 20 pixels is typically the size, so it's a nice square. And if you have a specific pattern made, You can further create further structures of the same easily by copy paste, and have a look at the aspect of it by changing your zoom levels, what the result is. So this type of visualization software is not doing much more than these kind of right. Yeah. So you can add another rule. If a cell is empty, give it another color, and you start to have aspects of how garments would look like, made with a specific pattern. And you can make your own more complex pattern independent of visualization software. Of course, yeah, it's clear that using, where is my, using a software that immediately shows this in a repeated pattern is of course advantageous. Yeah, but it is not a lot of work. I just want to indicate to predetermine a bit before you go to TextGen the sort of woven structure you might want, and you can set you can change sizes of in your by, if you go to your construction, suppose you want to work with a warp yarn that is thicker every three, and you can make a thicker version in order to have an effect. What is the effect a bit of this thicker warp yarn being used or a thicker weft yarn being used? And you just are working in Excel or Google spreadsheet in order to do that. Okay. So that's how this visualization software works. The more modern ones then allow you to work with color and further special cases around it. Now that you know what weaving is, what the basic weave types are, and how you can get some representation of it, of what the structure would be, let's have a look at the different ways that people are weaving. This is done with a number of looms. Now, the old looms were all shuttle looms. This is the case that we have seen. The yarn is inside of a little container, which is called the shuttle, and this shuttle moves from left to right. Yeah. If the yarn is finished, you have to knot it to another bobbin, which is put into the shuttle, and you can continue weaving. Already in the 19th century, there were shuttle looms that could automatically replace yarn in the shuttle so that human intervention was not needed, all with mechanical action without computers. Nowadays, most weaving is done with shuttle-less looms. One of the big types which allows to weave everything you want and which is used for a lot of specialty clothing, specialty yarns is the rapier loom. And in the rapier, you see here an image. The yarn is taken into a gripper. It is brought up to the middle of the loom. And at the middle of the loom, another gripper takes over the yarn and brings it to the right hand side. So the left gripper takes a yarn, and it's really, I take a yarn, I give it to you, and I bring it to the other side. And this is continued all the time. Of course, this rapier has to accelerate, decelerate at the middle, and then the right one has to accelerate and decelerate. So there's a limit because of the weight of these parts, and there's an impulse moment, so there's quite some weight involved there's a limit at how fast you can do that without putting too much stress on your machine parts. But the big advantage is that if you have a very hairy, loose yarn that cannot move very fast, or a piece of metal, your yarn is a piece of metal, with a rapier, by changing the speeds and everything, you should be able to weave as good as everything. For industrial weaving, however, air jet an air jet, but we are speaking air jets of 1.3 Mach, faster than the speed of air. Sorry, faster than the speed of sound in air. That is, and this air jet propels your yarn forward, and then there are a number of extra blowers over the length of your fabric that propel the yarn further so as to reach the other side. Another shutterless loom is a projectile. You see here a projectile. It is in a rail system, and the projectile is pushed from, takes a yarn and brings the yarn from the left side to the right side. Then, of course, at the right side, the projectile is collected. There's a system to bring the projectiles from the right back to the left. But like that, if your yarn is on the left side on a bobbin, you can shoot projectile over projectile over projectile through the shed and weave like that. Then nowadays there's also the water jet. The water jet is a bit like the air jet, but it is water that is propelling the yarn from one side to the other. And you also have more advanced looms, like the I see I forgot an I. I will quickly correct this. Like the multi-phase looms. Multi-phase looms allow to, it's on a, this here one is on the drum, the warp yarns enter, and several sheds can be made over this drum so as to be able to have like several sheds open almost at the same time, and hence you can bring weft yarn in those sheds at the same time. So you can weave several wefts at the same time like that, allowing you, of course, to weave quite a bit faster, but you need to do the beating up then in some other way. Now, the standard weaving, of course, is well known in most companies that do weaving. The main interest in still working this out, in investigating this with tools like TextGen, is because of the specialty woven structures. In this, you are combining different types of yarn with each other. For example, here in this image, you see you have strip yarns, and you have, so they are strips, and you have a filament yarn, a round filament yarn, which is also added into your structure. And you are combining those two types of structure, and you need to investigate what the effect will be on your cover factor and how easily it will be possible to do that. Another way is when you do lamination of woven structure, then you create, this is not called 3D woven structures, but multi-layer woven structure. Multi-layer because each layer is independent of the other layers, but they are connected to each other with a glue or with or by stitches or by some other way, and this creates different woven layers on top of each other. But this allows you also to do specialty yarn, and you can look at the fact if where the covering will be, the connection points will be of one layer to the next layer, if this is well dimensioned for optimal connection. Then, as specialty yarn, you have the 3D woven yarns. There are a lot of different types. I think the number of patents on different machines to create different forms is huge. I have shown you how with almost a standard weaving loom, you could do a sort of 3D woven structure. Here is different types. These are the hollow woven fabrics. and you can see that this is done. It's perhaps I need to find a clearer image. So here you have red yarns, and the red yarns run through, but they combine with the green yarns of the top. So you are weaving two layers with each other, independent, and then suddenly you will combine what you are weaving with one structure with what you are weaving with another structure in order to make these cross sections over the thickness of your yarn. And you have different types. You have it with the flat texture at the top. You have it with different textures at the top. And this is used a lot for composite construction, in which the composites, the resins to make composites are only done not in the hollow structures, but in the where the fabric is, and it creates, like here you see, a bended one and a straight one on top of each other, made completely rigid. So those are the hollow woven structures. You have another type, which is the multi-layer weave. In this case, you have 3 sets of yarns, warp, weft, and Z yarn. And these Z yarns are the dashed line here, and it connects one layer, and the top layer here is connected with the layer under. And like that, every time, different layers. You have a standard woven structure, but this Z yarn is connecting one layer with the next layer. And this can be done in different ways. So here it's double done. And yes. Another. Yetana, you were not muted. Okay, so then you have the 3D woven orthogonal woven fabric. The orthogonal woven fabric is also called the no crimp woven fabric, because what you have here, you can see that in this construction, you have a straight line in your warp, you have a straight line in your weft structure, and then you have your Z yarn, which are also called binder yarns, which go from the top to the bottom every time, top to bottom, top to bottom, yeah? Because of that, every section except the binder yarn rotating here at the top and the bottom, every section is straight. And because every yarn is straight, your crimp in those yarns is the minimum that is possible. So there's no crimp. So if you put it on a tensile tester for elongation, then immediately the yarns are stretched and you have the maximum of rigidity that would be possible. And because many composites are made to be high strength, this is advantageous for many applications. Then you have the interlock fabrics. So the interlock fabrics have binder yarns, so the warp and the weft are straight. You have binder yarns running under angles between them. Then it's called interlock. So this is just one layer to the next layer, but the left image gives an interlock over every time from the bottom to the right, but not orthogonal, but under an angle. And this is called angle interlock. Now, when yarns are placed into a fabric, they will deform. And there's nothing you can do about it. The only yarns that don't deform are monofilament yarns that are, let's say they are round, they have a form, and they would need a lot of stress in order to start to deform. So typically they don't deform. If you add monofilament copper yarn to a fabric in order to create a smart textile structure, it will remain round, it will remain the same. However, real yarns, they deform. You have, for example, here to the left is called the racetrack cross section of a yarn. Here to the right, it's called a lenticular cross section of a yarn. And you can investigate for here, for example, the image is an image we have taken with a microtome. So a microtome is you put your fabric in a resin, you make it hard, and then you make a small slice to put under a microscope, and you can see that is a blend of cotton and polyester, and the cotton is this light gray, which is a little bit deformed every time because cotton is not nicely round. And you can see that this cross-section in a standard, this is a plain weave, goes towards this lenticular cross-section. So if you are just looking at the visualization software, we just do black and white. But if we will go to more modeling, what is the aspect in reality with a tool like TextGen, then you need to know in advance what will be the cross-section of my yarns, because they will start to deform. Is it racetrack? Is it lenticular? So you need to investigate this for your woven structure, what cross-sections come forward, and then in TextGen, you are able to set these cross-section values. Now, what is done here at Ghent, we have a simulation also of the weaving tools. This is a simulation of weaving. You can see here how in airjet weaving, you have a pre-winder which has yarn on it. And here the jet starts from the right-hand side and the yarn is taken off the pre-winder. And you can see that in a simulation that there is a very good correspondence of how this yarn is behaving. So simulation of the weaving is something that is possible, and there's high interest of the machine producers of that. However, what we will be doing in this course is not simulation of the weaving, but simulation of the fabric as it is made after weaving. So the modeling that we do in case 4 of the course is woven structures. So you can import what you have made as a woven structure, which can be a standard woven structure or a braid. A braid is a special form of weaving almost. It's also interlacing. It's not weaving. It's completely different machines. But you can import those parts into modeling software, like for example, Abacus, and then simulate what the effect is of adding stresses to it, extension or compression or heating, etc. Now, case 5, which is will not be covered in this session, is about complex weaving patterns. If you have complex weaving patterns like this one, which is a tartan, or adding images to fabrics through weaving, all these kind of things are possible, but it is of course more oriented towards fashion than it is oriented towards technical textiles. If you look at this tartan case here to the right, this is called a tartan weave. How can this be made? For that you need a word diagram with pivot lines. You need a weft diagram, how the weft will be put in. So you will put, the warp is pre-made with red and white yarns, red and white, red and white. The weft here is red and white, red and white. That will be put into the shed. So that will be used as a weft diagram. So you have 2 types of yarns of 2 colors. And by weaving this, you can play with the coloring. And you see here the result where the red with red combination is red, but red with white creates more a pinkish color. So you can generate in between colors by doing that. Here to the right is giving with Arach weave a result of using 3 colors, green, white, and red. And this allows to obtain pure white, pure green, more blackish color of green on green, etc. Yeah. So that is how, by not only working with the weaving pattern, but by working with the colors of the yarn that is used, you can generate towards the consumer very different types of woven structures, also in color aspect. Of course, a very difficult thing to model color is that you have absorption, you have reflection, you have the light source, or you're in the sun, or you're indoors, and all this will, in reality, change the results still quite a bit as opposed to what the modeling software might have predicted. So the eating, of course, is in actually doing then creating the woven structure on a loom. In this last case in the course, we also look at image-based patterns. With image-based patterns, you create patterns based on, so here you see that this is a twill weave overall, but the pattern that you want is done with a sort of, it's more like a satin weave, it's not connected, but then in the weft. And so by changing on the loom how you are weaving, you generate a structure in your weave. So this is how this thing can be made, this image to the left can be made. Of course, this is very difficult on a standard loom with just where you are predetermining what you will do with the loom. The type of loom that is needed for this is a jacquard loom, which is a weaving loom in which every warp yarn can move independently of all the others. So every warp yarn is connected to a motor that can move it up or down to make a shed. This gives you full freedom in how to weave, but is also the most difficult to set up when you set up the weaving loom. Okay. Now, before we finish, what can we do with woven clothes? Let's have a look at the applications. The biggest application everyone knows is the clothes and the jeans. And jeans is a nice woven structure. The shirts that people are wearing, costumes, a lot of pants are made with woven structures. Nowadays, we can weave with elastic yarns. So the elastic yarns give you woven structures which are elastic, which originally was not done. Woven structures like linen are typically very inelastic. You use knitted structures to have elasticity, but nowadays by adding elastan content to your yarns, you can make woven structures which are also elastic and which is quite fashionable. If you look at rain jackets, a lot of this is woven structures which is very fine in order to have it impermeable to liquids. Of course, you have extra coatings added for that, but the base structure on which you apply these coatings is very important for the final result. Then we have our household products. If you just look around you in your household, you will see that a lot of the things you are using are made with weaving. And you have your bed sheets, the kitchen towels, all sorts of towels. This is a special technique, terry towel, where you have special loops which are added with a special weaving technique. But also a lot of furniture has woven parts embedded, used for it in order to increase the comfort while still being sufficiently strong, which is an aspect of your woven structures. Composites, with all types of composites. You see here, this is a calendared woven structure, so not really woven, but this is already weaving together with knitting and all these 3D weaving structures. The boundaries between what is weaving, what is knitting starts to be very flu. But concrete reinforced structures exist. A lot of composites are made by a base carbon fiber woven structure, and you can see that on the coloring, that your woven structure still comes forward, but afterward it is injected with a resin, a thermoresin, that hardens out in order to put your in order to be able to create very specific structures. Geotextiles is a large application area of woven structures. You can see you have the mats against the roots of plants that you can buy. You have different types of stabilization mats, also used within construction works. You need very large areas, weaving looms or very ideal in order to make very large amounts of material that can be used for geotextiles in stabilization techniques. Then, of course, also smart textiles. We ourselves are more doing smart textiles. You can add glass fiber for lightning effects into your woven structure. You can add connection lines into woven structure so as to build up a circuit from your woven structure. Yeah, those are also applications, technical applications for woven material. So that is it for the first part. I think it might be interesting if you go to the course, and if you log into the course, if you go to design and modeling of woven structures, yeah, then you have your quiz of woven structures. I'm not fully, I think the quiz is not there. I need to go to, so we have seen the background for case 1, 2, and 3. So if you go to case 1, and I think it has to be the quiz there then. And next section. I thought there was a way to quickly navigate. So in the course, if you go in the course, you also find videos that give you some background on how to work with things. Rasma, now I don't, where is the quiz for the students? Perhaps because I did the quiz myself to test, I'm not seeing it.
Benny, just click on continue the last preview.
Continue the last preview.
Go back.
Yes, design.
There on quiz. No, no on quiz, on case on quiz. And below on this button, yes.
Okay, okay, yeah. So I would say, yeah, I would take a break of 5 minutes before then doing the practical work. But yeah, you should be able to do the first, I think 15, 12 questions. Yeah, try once part of the quiz. So the first part is quiz questions on case 1. The next part is on case 2. And the third page is on case 3. Okay, so try once the quiz based on, if you listen carefully, I think I said 80 to 90% of what is also in these modules. So I think most of you should already be able to do the quiz. Okay.